We'll have more talks about applications of amplitudes to gravitational waves, et cetera. And we are going to start with Carlo Heissenberg from Nordita, who's going to tell us about black hole scattering, Eikonal resonation, and gravitational waves. I'll give you a 10-minute warning, 5 + 5 questions. Okay, please go ahead.
Okay. Thank you, Julio. And let me start by thanking the organizers for the opportunity to present this talk, which is based on work done in collaboration with Paolo Di Vecchio, Rodolfo Russo, and Gabriele Veneziano on this recent note, and also some work in progress. So I hardly have to motivate the interest in scattering amplitude methods to apply to the calculation of post-Minkowskian expansions of classical gravity, thanks to the beautiful talks by Mao Zheng and also by Thibaut Damour, clearly emphasized how these type of techniques can help to push the precision frontier of these PM calculations and can be useful to obtain closed form results for gravitational observables. So the idea for this talk is to start by reviewing a little bit this framework, in particular focusing on a technique to extract classical information from scattering amplitudes via the Eikonal exponentiation. And then I will discuss a specific setup where this exponentiation is realized, and we have calculated to up to 3 PM order, so 2 loops on the amplitude side of the calculation. And N=8 will serve as a useful theoretical laboratory to illustrate many physical effects that also appear in the real-life general relativity calculation, in particular the interplay of these radiation, reaction, and potential effects. And then in the last part, we will discuss how these radiative effects can be actually calculated in general relativity via amplitude methods, in particular focusing on the 3-particle cut of the amplitude. And hopefully towards the end, we'll be able to mention how real radiation fits into this picture. So let me start by specifying a little bit more precisely the process we are considering. So we are discussing the scattering of 2 black holes here depicted by these 2 blobs, which we will, however, consider as point particles for our purposes today. And they collide with some impact parameter B or Bj, depending on slightly different geometrical interpretation. And distinguished observable we'll be focusing on today is this deflection angle chi, or almost equivalently this capital Q, which is essentially the transverse classical momentum transfer. And we want to consider a regime in which the black holes that scatter are in a classical regime. So we can enforce that by stating that the quantum wavelengths associated to these objects, say h⁻m for massive objects or h⁻ the energy for shockwave scattering. So these quantum wavelengths would be much smaller than their proper sizes, which are characterized by the Schwarzschild radii. And furthermore, we want to focus on the PM regime, so on the regime in which these gravitational interactions are actually weak, and therefore we have to impose that both these quantities are much smaller than the typical distance, let's say the impact parameter itself. So the idea is that we want to extract information from fundamental object, from which is the amplitude, in this case, this 2-to-2 amplitude depicted here, expressed here as a function of the Mandelstam invariant S and the momentum transfer Q. Let me emphasize that this momentum transfer small q is let me distinguish it from the other one by calling it perturbative, and it will be hopefully apparent soon what the difference with this classical momentum transfer is. So the first step that we need to do is that we need to recast the amplitude that we have in this momentum space representation and transform it to impact parameter representation. And this just involves a Fourier transform with respect to this small q. And since we are interested in the regime of large impact parameters, we are of course interested equivalently in the small q expansion of the amplitude. And more precisely, since we are interested in long-range terms in B space, we can safely disregard any analytic contribution in Q space. So let me write down the amplitude in the loop expansion and perform this large B expansion loop by loop order and see what we get. So here I'm stating the typical terms that we get, repackaging these dimensional full quantities into these lengths that I had introduced in the previous slide. So eventually, since we are interested in classical quantities, we would like to use the 1 over h bar as a guiding quantity in order to extract where the classical information is. However, as you can see, while the 3-level does indeed scale like 1 over h bar, so it's r over lambda, where lambda is proportional to h bar, and thus respects the standard power counting of powers of h bar, so h bar to the L minus 1, where L is the loop order. At higher loops, we find some slightly unexpected phenomena. So together with these quantum terms where h bar never appears in the denominator, we still have 1 over h bars here, and even higher powers of 1 over h bar, 1 over h bar squared, 1 over h bar cubed. So it's not clear how to proceed. We need a way to reorganize this perturbative expansion in order to, we need a guiding principle to extract the classical information. And this is provided to us by the Eikonal exponentiation. So in the classical limit, we expect the amplitude in momentum in impact parameter space to exponentiate according to this form. In particular, it should have the exponential of a large classical phase, reminiscent of e to the I over h bar classical action. And so this delta here, which we call the Eikonal, should be really proportional to r over lambda, so to 1 over h bar. And then on top of that, it should only have post-Minkowskian correction, classical post-Minkowskian correction proportional to r over b, which is the small post-Minkowskian parameter, to some power. And then downstairs, let's say, with respect to this exponential, there can be, of course, quantum correction where h bar never appears in the denominator. Now, how do we make contact between this formula and the usual perturbative expansion? Well, the only way we know how to do it is to re-expand formally this expression for small g, which is also clearly emphasized by Thibault towards the end of his talk, is actually not compatible with the classical limit, strictly speaking, but it's the only way we know how to do things. So we have to re-expand this exponential, and then we indeed get all these iteration terms associated to higher powers in the exponential series. And in particular, this first column corresponds to the leading Eikonal that was also mentioned in the Rachel Rosen's talk yesterday. And then there are also subleading objects that appear to higher loop levels, and from which we can in particular extract delta 1, the first correction to the Eikonal, and also delta 2, which is the 3 p.m. order I'm going to focus on today. So once we have reconstructed the Eikonal from the perturbative expansion in this way, what we can do is that we can go back from impact parameter space to momentum space, and notice that in this inverse Fourier transform, the exponent is a largely oscillating phase. Let me remind you that delta is a classical quantity, so it's large in the sense that 1 over h bar is large in the classical limit, and therefore the integral is dominated by the stationary phase approximation, which determines this classical momentum transfer Q as the derivative of the real part of the Eikonal. So here, the difference between this momentum Q and the small q I was talking about earlier becomes apparent, since Q is a classical quantity, while the small q, the perturbative momentum transfer Q, is of order h bar over b. So it's really a quantum, small quantum quantity, and this reflects the fact that in the Eikonal, the exchange of many gravitons with perturbative momentum of order h bar over b is resummed, and therefore the final momentum transfer turns out to be classically finite. Now, here I'm, of course, once one has determined this capital Q, it's very easy to determine the deflection angle we are after. So here I'm just giving a schematic form of how the dimensionful quantities arrange themselves in this type of calculation at the first few PM orders. And indeed, for instance, the 3 PM calculation will be proportional, scattering angle will be indeed proportional to r over b cube. And the non-trivial task that we have, that we face, is to calculate the precise dependence that is in front of here on the velocity of the two bodies, or equivalently on this Lorentz factor, relative Lorentz factor sigma, which is nothing but 1 over square root of 1 minus v squared, where v is the relative velocity. Let me also mention a subtlety before moving to the next part. So up to 1 PM order and 2 PM order, this Eikonal is indeed a phase, but starting at 3 p.m., it also acquires an imaginary part, in fact, an infrared divergent imaginary part, which is linked to the appearance of a three-particle cut involving soft massless particles. And this, in fact, will be important for the last part of the talk, but for the moment, let me neglect it. I promise you that the real part, which is the only one intervening in the stationary phase approximation, is going to be finite. So let me worry about that later. So let me now move to a concrete setup where all this can be checked and realized, which is an equalizer for gravity. As I anticipated, this is a useful toy model, or more precisely theoretical laboratory, in the sense that, yes, of course, amplitudes are simpler, but still this setup really has the same physical phenomena showing up and can teach us a lot about what happens in the real gravity setup. So here I'm giving the schematic form of the amplitude to the two loop orders we are interested in, and already expanded for small q. In fact, I'm already neglecting some terms that are further suppressed in the small q limit. So the task at hand is to evaluate integrals of this type, where this blue line and red line are the massive lines associated to the two massive particles that scatter, and here there are some exchange massless particles. So here I'm just picking one of these integrals for concreteness, and the issue is to evaluate the limit of small q, and luckily we can apply the well-established technique, which is the method of regions, to perform this limit. As also discussed by Mao, two regions appear in particular in this calculation. One is the hard region, where the momenta, integrated momenta or loop momenta, essentially do not scale with q, but this just gives rise to analytic terms in q squared, which are really relevant to the long-range behavior, and we can throw them away. The relevant region is the soft region, where the loop momenta scale as q, and indeed this gives rise to these non-analytic terms in q squared, and therefore to these power law long-range terms in the B-space in the B-space expression. And to evaluate this type of integrals, Julio, Michel, and Mao have developed a beautiful technique based on differential equations. So schematically, one identifies a basis of soft master integrals, so master integrals that are really tailored to these soft region calculations. And once one has done that, one can expand any of these integrals into these master integrals. In turn, the master integrals obey ordinary differential equations, which can be put to this order in the Hahn canonical form. And so really the only thing left to do is to evaluate the boundary conditions. And we evaluate them for sigma going to 1, which is the static limit if you want velocity going to 0. Here, again, for completeness, I've just written down one of these master integrals in the Schwinger parameter representation. And the way we can go about evaluating this limit is once again by the method of regions. So here, for convenience, in the Schwinger parameter setup. So we distinguish two regions in this limit. One we term ordinary region, in the sense that one simply sends the velocity to 0 inside the integration sign. And this type of contributions typically are real and finite. On the other hand, there is another region which is important, in particular in order to get radiation reaction effects right. And this is this singular region in which one needs to assign a non-trivial scaling, in particular with respect to the velocity, to this intermediate line 3, which, as you can see, is precisely the one intervening in the three-particle cut. And this is no accident, since indeed these contributions are those that are important to capture the imaginary part of the boundary conditions. So let me show you the final result. We find the Eikonal, which takes this form. The real part is IR finite as promised and contains two types of contributions. One type is given by the potential contributions. These are just conservative, express the conservative interaction due to the mutual gravitational attraction felt by the black holes via the mutual gravitational potential, while these contributions in blue, these new contributions in blue, are associated to radiation reaction, to the fact that the black holes radiate and therefore feel an effective radiation reaction force. And in fact, as also mentioned by Thibault, the interplay between these types of contributions is crucial in order to restore the agreement of this result with the high energy limit. In particular, the potential contributions alone will have an enhanced a logarithmic enhancement with respect to the known universal ultra-relativistic limit, and instead the sum of the two precisely reproduces the agreement with the result. In particular, the result is by Amati, Ciaffaroni, and Veneziano. Let me also mention a hint towards the extension from n equal 8 to GR that is already in this slide. So if we look at this imaginary part, we find two types of objects that could hint towards how to go about the calculation in GR. So we find this logarithm here and this 1 over epsilon. So in fact, the logarithm of sigma squared minus 1 can be shown by analyticity and crossing symmetry to imply the presence in the real part of delta of contributions that have precisely the same factor in front. And in fact, as you can see, really the same factor is highlighted in blue in both formulas. So the idea is that if we manage to calculate these type of terms, we already know also the radiation reaction contributions that should sit here. And so schematically, the reason is that this logarithm in the imaginary part should correspond in the real part essentially to a factor of pi by analyticity. And the idea, therefore, is that we could target the calculation of these radiation reaction contributions separately in the GR case using unitarity. In particular, the 3-particle cut is sufficient in order to capture really the imaginary part of delta 2, which is the one we are after. So this 3-particle cut involving 3-level amplitudes to disorder that I'm drawing here. So in the last part, I will try to illustrate these type of calculations. The first ingredient we need is that this 5-point amplitude I'm talking about here. I'm just showing it for concreteness. Of course, I don't want to enter too much into details. So we basically need this amplitude. We need to stick into some appropriate square involving this intermediate, let's say, projector pi. And let me emphasize that by suitably choosing beta and pi, one can keep both theories under control. So one can go easily from n equal 8 and GR by suitably changing the expression for these quantities. So this is useful because one can, on the one hand, cross-check everything with the explicit calculation n equal 8, and on the other hand, also get the GR result. Once one has constructed this object, this square, one of course gets some rational function, and the useful strategy is to treat the delta functions, the phase space delta function that appeared here as cut propagators and really manipulate them in an algebraic fashion in a very similar way with respect to the standard propagators. And in this fashion, one can reduce the calculation to this type of cut topologies here. And at the very end, these topologies can be expanded in the same master integrals as discussed also by Mao yesterday. The same master integral as the full soft calculation up to a suitable change of boundary condition. And this is really the strategy, the very useful strategy of reverse unitarity that allows you to calculate this, in principle, rather complicated phase space integrals by ordinary differential equation tools. So let me arrive to the final expression we get. So here in this slide, what we get first is now instead the second half of the slide, this imaginary part here, and for GR. Of course, for n equal 8, we simply reproduce the result I showed you in the previous slide. For GR, we do indeed get these logarithmic terms I was mentioning earlier, and therefore, by using analyticity and crossing, we can infer from this expression here the corresponding expression for the radiation reaction terms in the real part of delta, which, let me remind you, eventually leads to the deflection angle. Let me now mention a further simplification to this type of strategy that actually historically was the one first proposed. So instead of looking at this logarithm, it's actually simpler to determine the 1 over epsilon terms. And the reason is that these terms can be targeted either by restricting to the soft exchanges in the 3-particle cut, or they can be targeted also by using the exponentiation of infrared divergences. So let me try to illustrate these two methods. So the first one is, again, let me write down this 3-particle cut here. And the idea is now to focus on the 5-point amplitude in the Weinberg limit. So taking not only this classical limit q much smaller than m, but also the momentum of this associated to this red line much smaller than both of them. In this regime, of course, as was also discussed, I think, this morning, depending on your time zone, at length, there are powers of soft theorems that, for instance, the Weinberg one is one of the most famous, and this is the only one we need, in fact, to perform this calculation. We can use this factorization in the soft limit, stick it into the three-particle cut, and here I just want to focus on the piece from where the divergence arises, which is this integral over the frequency here. Of course, this comes with this 1 over epsilon in dimensional regularization, but it is also accompanied by a logarithm of the cutoff frequency omega max. And the reason why I'm emphasizing this is that
5 minutes. Carlo.
Okay, thanks. So for small velocities, we can argue that this omega max is in fact proportional to v, and this, as you can see, if we extrapolate to higher to larger energies, we get precisely the right coefficient between the 1 over epsilon and the log that we get in the full expression. So the bottom line is that instead of determining the log, you can indeed determine the 1 over epsilon because they appear with the same coefficient, apart from this minus sign. Equivalently, we can target these 1 over epsilon terms in the imaginary part by exponentiation of infrared divergences, and in fact, two very similar exponentiations occur both in n=8 and in gravity. Let me not go into details here, but of course, the bottom line is that one loop infrared divergences exponentiate and allow you to determine this imaginary part, this divergent part, by using lower loop data. So the two-loop divergent part using lower loop data. So let me just say in one formula what is the bottom line of the second half of the calculation. The bottom line is that if you manage to calculate the imaginary part of delta 2 in some way, the divergent part, you simply multiply it by minus 2 epsilon, and this gives you the radiation reaction terms. In the last remaining minutes, let me also mention something that connects to real radiation. So up to now, I've been interested in the 5-point amplitude just because it appears in the cuts of the elastic amplitude. But of course, the 5-point amplitude is also important on its own. In fact, up to rewriting in impact parameter space and the Fourier transform with respect to the frequencies, it also gives you the waveforms to leading orders. So the coefficient of the asymptotic metric fluctuation, the coefficient of the 1 over r. And this, so we have also performed this calculation. And let me just flash the result we get for the two polarizations here. We are in the process of performing some comparisons with the recent results by Jakobsen, Mogul, Plevka, Steinhoff, and Mugia, Kakos, and Vernizzi, and also with the classic paper of Kovacs and Thorn. Let me also emphasize that up to now, all the constraints that are due to soft theorems, constraints related to the large U behavior of the amplitude that have been pointed out by Sen and collaborators also seem to be satisfied. So let me very conclude with an observation that has to do with combining the elastic exponentiation I've been dealing with these inelastic amplitudes that are also important to determine the gravitational waveforms. So in fact, already the presence of this non-trivial imaginary part is a bit suspicious and clashes with our expectation that the exponentiation should give you something unitary. It hints the fact that we are really neglecting some channel, and therefore we get this exponential suppression. And the right way to restore the unitarity in this setup is probably to combine the Eikonal, the elastic Eikonal with some inelastic exponentiation in order to construct some Eikonal operator. Let me just report some zeroth order progress in this direction, which is a check that in the n=8 massless case, the one loop amplitude seems to be compatible with a first exponentiated structure of the type 2i delta 0 times the 3 level one. So let me conclude by putting on the screen this sort of flow chart or progress chart of things that have been done and are being done or hopefully will be done sometime in the future. So what has been done is the 3PM Eikonal, essentially complete of its imaginary and real parts, potential and radiation reactions, both in n=8 and in GR. Radiation reaction has been obtained by various amplitude-based methods, which agree with the calculations of Thibault, for instance, using purely classical methods. For instance, suitable combinations of analyticity, crossing, unitarity, and higher exponentiations, and also leading order waveforms are fully under control, also due to the works I have cited in the previous slides. We are in the process of understanding a bit more about this inelastic Eikonal, which we expect will be crucial in order to extend the Eikonal program to higher PM orders, hopefully sometime in the future. Thank you very much for your attention.
Okay, thanks a lot, Carlo, for a beautiful talk. Are there any questions? Okay, I see Gustav has raised his hand.
Thanks, Carlo. That was a really nice talk. I'm a little bit curious. You'd mentioned these, you've been looking at these waveforms, which we also looked at from these 5-point amplitudes. And I saw what looked like some Bessel functions there in those expressions that you flashed briefly. So I remember we had those, we were looking at those for a while when we were in the frequency domain, but then we didn't like them. So that was why we moved over to the time domain. You have to, have you figured out how to integrate those Bessel functions? Have you, I'm just curious.
Yeah, I agree that they are simpler eventually in U space if you do this integral that I've written here, right? The reason why I've shown here the omega expression is that the first one that you obtain in order, because we work, you know, in our approach, we really obtain the first, okay, for the fully momentum space expression, then we have impact parameter and k if you want. So we really get this here from this approach, and then we have to perform the Fourier transform at the very end. So these two expressions are the ones that are a little bit more under control at the moment. But we also have, I mean, we have already done these integrals, and most of them appear to be doable and to simplify, as you say, the expressions. But okay, there may be still more typos in those terms. That's why I was showing these ones.
I mean, I'm just looking at, for instance, this 0,1 integral dx of k0 in the last line down there. You know how?
Yeah. I think maybe Paolo or Rodolfo, if they're online, can correct me. But I think if you perform the integral with respect to omega, these integrals simplify. So, you know, if you commute the integral with respect to omega with this integral with respect to x, then you get a simpler integral that you can do.
Okay, but it's using the Fourier transform again.
Yes. After going to U space. Yes.
I see. Okay. Thanks.
Okay, we have time for one more quick question. I think David raised his hand first.
Thank you. Congratulations on this overview of very up-to-date work. I was very intrigued by a reference to work in the 70s done by Kovac and Thorne. Can you just go back to that slide and say what part of what you were doing they had done then?
Yeah, basically they had the expression for these waveforms already then. They were much less compact, and some of the results were PN expanded, so we're not. Some of the expressions were expanded for small velocities, but I think if one digs deep enough in those papers, the information is already there. Maybe Gustav and the others can correct me if I'm wrong. Basically, they had already calculated by purely classical means these waveforms.
Very good, thank you.
I mean, essentially, basically what they did is they solved the classical equations of motion for the theory.
Exactly, by purely classical techniques.
Very much brute force, using some quite old-fashioned methods. I mean, the results are there, but those papers are, I will admit, a little tricky to read at times.
Yeah, exactly. That's why I was saying if one digs deep enough.
Anyway, thank you for making the connection. It's much appreciated.
We started 2 minutes late, so Mao, if you still want to ask your question, if not, we can move on.
We can talk afterwards.
Okay, great.
Okay,
so
sure.
Let's thank Carlo again.